Section 5.3 is a very interesting one. It's about selected topics from number theory. And so we'll be talking about perfect numbers, deficient and abundant numbers. I'm going to skip part 3. We state and evaluate examples of Goldbach's conjecture, and then we talk about twin primes, and then we state and evaluate Fermat's last theorem. So these are all very interesting topics, and we begin with perfect numbers. And so the definition of perfect number is that it is perfect, said to be perfect, if it is equal to the sum of its proper divisors. So the proper divisors are all the divisors of a number except the number itself. Okay? So as an example, let's look at this little exercise here. The proper divisors of the number 496 are 1, 2, 4, 8, 16, 31, 62, 124, and 248. Use this information to verify that 496 is perfect. So all we have to do is really add up all the proper divisors. So it's 1 plus 2 plus 4 plus 8 plus 16 plus 31 plus 62 plus 124 plus 248. And so 1 plus 2 is 3, and 4 is 7. 7 plus 8 is 15. 15 and 16 is 31, plus 31 is 62. Plus 62 is 124. Plus 124 is 248. Plus another 248 is equal to 496. So the sum of the divisors equals the number, and therefore 496 is a perfect number. The next exercise consists of several parts. As mentioned in the text, when 2 to the n minus 1 is prime, then 2 to the n minus 1 times 2 to the n minus 1 is perfect. By letting n equals 2, 3, 5, and 7, we obtain the first 4 perfect numbers. Show that 2 to the n minus 1 is prime for n equals 13. So let's do that. So when n equals 13, then 2 to the 13th minus 1 would be 8,192 minus 1, and that's equal to 8,191. And that number is prime. Now for the B part, to find the decimal digit representation for the first and for the fifth perfect number, let's proceed like this. From the A part, let's proceed with this. 2 to the n minus 1 times 2 to the n minus 1. So we know that for n equals 13, this is a prime number. So therefore, we would have 2 to the 13 minus 1 times 2 to the 13th minus 1. And we already computed this number, 2 to the 13 minus 1. That's 8,191. And 2 to the 13 minus 1 is 2 to the 12th. And 2 to the 12th is equal to 4,096. So when we multiply these two numbers, we get the number 33,550,336. So that is the fifth perfect number. The next topic is deficient and abundant numbers. So a natural number is deficient if it is greater than the sum of its proper divisors, and it is abundant if it is less than the sum of its proper divisors. So for number 17, the proper divisors of 32 is 1 and 2 and 4 and 8 and 16. And the sum of the proper divisors is equal to 31. So therefore, we say that 32 is deficient. Now when we look at 60, the sum of its proper divisors, so its proper divisors are 1 plus 2 plus 3 plus 5 plus 10 plus 20 plus 30 which is equal to 71. So in other words, the number 60 is abundant. So the proper divisors of 84 are 1 and 2 and 4 and 7 and 12 and 21 and 42, and all that adds up to 89. So therefore we can say that 84 is abundant because the sum of its proper divisors is greater than the number itself. And let's look at number 75. And for the last one, 75, its proper divisors are 3 plus 5 plus 15 plus 25, and that's equal to 48. So therefore, we can say that 75 is deficient. As we try out the different numbers between 1 and 25 that are even, eventually we find that 12 is abundant because the proper divisors of 12 are 1, 2, 3, 4, and 6, which adds up to 16. So that means 12 is abundant. And then the next one, as it turns out, is 18, because 18, the proper divisors of 18 are 1, 2, 3, 6, and 9, and that adds up to 21. And then the next one is 20. Its proper divisors are 1, 2, 4, and 5, and 10, and that adds up to 22. So 20 is abundant. And then, excuse me, 24, its proper divisors are 1, and 2, and 3, and 6, and also 8, and 12. And that adds up to 36. So it is certainly an abundant number also then. So these are the 4 abundant numbers: 12, 18, 20, and 24. And then there's a statement, a prime number p must be deficient because the sum of its proper divisors is 1, which is less than p. So the answer here is 1. The next concept is that of amicable or friendly numbers. And the natural numbers a and b are amicable or friendly if the sum of the proper divisors of a is b, and if the sum of the proper divisors of b is a. And so here's a statement that 220 and 284 are the smallest pairs of amicable numbers, and then the next one would be 17,296 and 18,416. That's the next smallest pair of amicable numbers. So let's examine this for 220. So for 220, the proper divisors are 1 and 2 and 4 and 71 and 142. So its sum is equal to 220. So these are the 284. So its proper divisors are these, and the sum is 220. And then we look at the the proper divisor of 220. So the sum of the proper divisors of 220 is 1 and 2 and 4 and 5 and 10 and 11 and 20 and 22 and 44 and 55 and 110. And all that adds up to 284. So it's an example that 220 and 284 are amicable numbers. To prove it for the other two numbers, that takes a lot of space and a lot of time and a lot of work. So we won't do that here. Christian Goldbach was a mathematician who lived from 1690 to 1764, and he made a statement, it's a conjecture, in other words, well, one has not been proven to this day, that every even number greater than 2 can be written as a sum of two prime numbers. So that has not been proved in general. All mathematicians, it's a very famous conjecture, but so far has not been proved. But it has been proved for numbers as large as 4 times 10 to the 18th power. So a lot of work has gone into that, but the actual proof has not been, has not been developed. And here's some examples, like 8 as an even number. It can be written as 5 plus 3. Or 10 can be written as 5 plus 5. Or 7 plus 3. So in other words, it's not unique. As example, the example for number 10 shows. So then we're supposed to look at the even number. And we're supposed to write 12 as a sum of two primes. And it says even in general there may be more than one way to do this. So for example, 12 we can write as a sum of the two primes 5 plus 7. And 24 we can write as a sum of two primes such as 7 plus 17. And 40 we can write as a sum of 11 plus 29. And 54 we can write as a sum of 7 plus 47. So you just have to think about this a little bit and try different combinations, and eventually you come up with the right answer. Of course, there are other ways to write, for example, 24. We can write it as 5 plus 19. Another one would be 11 and 13. So these are, again, more than one way. And 40 we can write in a couple of different ways in addition, like 17 plus 23 and 37, or 3 plus 37. So it is not a unique representation. And similar ways can be found for 54. I leave that up to you to work on that a little bit on your own. Then there's a topic called twin primes, and those are prime numbers that differ by 2. So they're called twin primes. For example, 3 and 5, 5 and 7, 11 and 13, 17 and 19, 29 and 31, etc. So there are a lot of twin primes, and that's primarily to understand what's meant by that. It's pretty intuitive, I think. Remember when we proved, we traced the Euclid's proofs that there are infinitely many primes? We used the expression p sub 1 times p sub 2 times p sub 3 times p sub n plus 1. So when all the primes up to p sub n are included, the resulting number, or numbers a prime, are called primorial primes. So as an example, when they are denoted by this p and then a pound sign plus 1, plus or minus 1. As an example, let's look at the one for 5. Example, for 5, by primorial plus 1 would equal to, would be 2 times 3 times 5 plus 1. So that would be 30 plus 1 equals 31. And that, of course, is a prime number, but that's also a primorial prime. And you can go to table 5 on page 201 in the book, and it shows you the largest known, the greatest known primes, several types. And some of them have, well in the hundreds of thousands and even millions of number of decimal digits. So some very large numbers, and probably took a long time to discover them. So these are the primorial primes. So let's verify the formula plus 1 for p equals 3. See if that produces a prime number. So in other words, that would be 3 plus 1 would be 2 times 3 plus or minus 1. So with the plus, it would produce the number, well, with the minus of 2 times 3 is 6, minus 1 is equal to 5, and with the plus sign, it's equal to 7. So they're both primes, of course. And not only that, they're twin primes. I just corrected a typo here. It's primorial primes. And this is plus or minus 1. A little bit hard to read. To talk about Fermat's last theorem, let's think about the Pythagorean theorem, which says that a squared plus b squared equals c squared. We're familiar with that. And that, of course, works for a lot of triples, like 3 squared plus 4 squared equals 5 squared. In fact, there are infinitely many triples for which that works. Well, so then the question is, can we generalize that like a to the n plus b to the n equals c to the n? So that was a great question that people investigated, and so Pierre Fermat, he made a statement many hundreds of years ago, and here's his very famous theorem. For any natural number n greater than or equal to 3, there are no triplets a, b, and c that satisfy the equation a to the n plus b to the n equals c to the n. So initially, he thought there were not infinitely many, but it turns out there's none even for n equals 3, greater than or equal to 3. So, but that's a theorem which was finally proved in the 1990s. So it took quite a few years to do that. I mean, he made this claim in the 1600s, so it was like 300 plus years later that the proof was finally developed. So obviously a lot of work has gone into that, and he also we can say that here's how it's applied, that every odd prime can be expressed as a difference of two squares in only one way. So let's do that. Let's find one way for the prime number 5, and then find one way for the prime number 11. So as you're thinking about the different possibilities for 5, you say, okay, maybe 5, I can write that as a difference of 9 minus 4, and so that would be 3 squared minus 2 squared. So it would be the difference of 2 squares. Similarly, 11, think about squares like 36 minus 25, or 6 squared minus 5 squared. So it's a unique representation, the difference of 2 squares. So in other words, 3 squared minus 2 squared, and this is 6 squared minus 5 squared. And this concludes section 5.3.